안녕하십니까? 바쁘신 시간에 오늘 저희 컨데어 웨비나를 참석해 주신 여러분께 먼저 대단히 감사드리는 말씀을 드립니다. 저는 오늘 컨데어 웨비나를 진행을 맡게 된 지형철이라고 합니다. 저는 컨데어 쪽에서 이제 한국 쪽에 세일즈를 총괄하고 있습니다. 저희 프레젠테이션 끝에 제 이메일 주소와 제 연락처를 넣어드렸으니까 혹시 필요하신 분들은 나중에 저한테 메일을 주시면 제가 따로 피드백을 관련 회신을 드리도록 하겠습니다. 그리고 오늘 프레젠테이션을 진행을 하시게 될 저희 프레젠터 데이브 볼씨에 대해서 잠깐 소개 말씀을 드리겠습니다. 저희 데이브 볼씨는 저희 컨데어 세일즈 글로벌 팀 소속이시면서 이제 애플리케이션 매니저로 활동을 하고 계시고 글로벌 쪽에서 이제 스페셜 프로젝트를 직접 서포트를 좀 해주고 계십니다. 그리고 특히 저희 모든 컨데어 가습기뿐만 아니라 증발 가습 솔루션에 대해서 굉장히 많은 경험과 지식을 보유하고 계십니다. 저희 오늘 금일 웨비나는 약 45분 정도로 이제 영어로 진행될 예정이고, 그리고 후반부에 약 15분 정도의 이제 Q&A 세션을 저희가 마련했습니다. 그래서 혹시 질문 있으신 분들은 저희 고추 웨비나 툴에 보시면은 퀘스천 질문하는 툴이 있습니다. 그쪽에 직접 한글로 이렇게 직접 질문을 적어주셔서 전송해 주시면은 나중에 Q&A 세션에서 저희가 소개를 해드리고 직접 피드백을 드리도록 하겠습니다. 그리고 일단 저희가 웨비나를 시작하게 되면 이제 오디오는 이제 뮤트로 자동으로 전환되고, 그리고 혹시라도 사운드가 지금 안 들리시거나 오디오에 문제가 있다고 생각하시는 분들은 저희 고토 웨비나 쪽에 보시면 이제 오디오 탭이 있거든요. 그 오디오 탭에서 디바이스를 다른 걸로 선택하시면 아마 해결을 할 수 있을 거라고 생각됩니다. 그리고 참가자분들의 이제 편의를 위해서 저희가 본 프레젠테이션 파일을 포함해서 총 4가지의 이제 파일을 이제 업로드 해줬으니까 다운로드 해주시면 감사하겠습니다. 그리고 본 웨비나에 참석하신 분들 중에서 이제 외국에서 직접 로그인 하신 분들도 계셔서 제가 간단하게 영어로 소개 말씀을 드리겠습니다. Thank you for joining us for our Condair webinar using humidifiers for evaporative coolings and in handling units. My name is Jeff G. I'm a business development manager. I'm in charge of Condair Korean sales. And with me today, I'd like to delightfully introduce our presenter, my colleague, Dave Bull, Mr. Dave Bull. He's an application manager, and also he's doing a lot of works for global technical support as a special project manager. He has long years of good experience and knowledge in terms of our all humidification solutions and products, including evaporative coolings and products. This webinar will be around 45 minutes, and we also have 15 minutes of Q&A session later on. So if you have any question, you can type your question and send us so that we can raise your question at the end of our Q&A session. If you have any problem in audio, you can also choose with another audio tab to solve your problem. And we also attached 4 files for your better understanding and consideration. So you can feel free to download our presentation file and some brochures. Okay, then I will turn over to our presenter, Dave. Dave?
Thank you very much for the introduction, Jeff. I'll turn my camera off at this point so you can concentrate on the presentation. Sorry. Okay. All right. So yes, as Jeff mentioned, today's topic is using air humidifiers for evaporative cooling in air handling units. So a brief overview of the topics we're gonna look at today. So firstly, we'll talk about the physics and the benefits of evaporative cooling. So how it works and why we would do this. Then we'll look at 3 individual different types of evaporative cooling. So different ways we can utilize the principle of evaporative cooling in an air handling system of differing configurations. Now that will make sense more as we start to talk about it, because we'll start to see how we can use it in different climates around the world. Then we'll talk about different types of evaporative cooler technology, the advantages and disadvantages of each type, and then we'll just look at some online tools that Condair can provide you for working this out. So in terms of evaporative cooling, how does it work? So what we're effectively doing is we're getting water to evaporate. So to get water to evaporate, we require energy to have a change of state from liquid to a vapor. So with something like a steam humidifier, for example, we're adding energy in the form of electricity. So we're adding electrical energy to the water to take it from 20 degrees up to 100 degrees. And then we're adding additional energy to force the change of state from a liquid to a vapor. So for the latent heat of vaporization. So we're adding all that energy to change water into steam. With an evaporative humidifier, or an adiabatic humidifier, as it's also called, we effectively have to do the same thing. We have to get water to change state from a liquid to a vapor. Now, an evaporative humidifier or an adiabatic humidifier, it might be a wetted pad, as you can see here in the picture, where water is run down over a media, and as air passes through, the water evaporates and it cools the air. Or it could be a spray type system, where we're spraying small droplets of water and they're evaporating. But whatever method it takes, what we have to do is get water to change state from a liquid to a vapor. So the energy for that change of state comes from the air itself. So that's why we get a cooling effect from evaporating water. We're taking the energy from the air to change the state from liquid to a vapor. So for every approximately, and it obviously it depends on the temperatures, approximately for every 1 kilogram or 1 litre of water you evaporate, you get 680 watts of cooling. And obviously, as I said, this will vary slightly depending on water temperature, etc., etc. So you can see you can get quite a large amount of cooling just from evaporating 1 litre of water. So that's the advantage. The main advantage of the system is going to be in the high capacity cooling for low energy consumption when compared to a traditional chilled water or DX cooling system. But probably the limitation of evaporative cooling is that you do need an initial low humidity to allow moisture to evaporate. So if you are in a tropical climate with 80–90% relative humidity, that's going to limit the amount of water can be evaporated, and so it's going to limit the amount of cooling that you can get. But even in these climates, there are ways that we can get around that problem, and we'll discuss those briefly at the end of the presentation. So next we come to our old friend, the psychrometric chart. I'm sure most of you have seen these, but for those of you that haven't, a psychrometric chart is what air conditioning engineers use to calculate heating, cooling, humidification, etc. So we have various lines on the chart. We have along the bottom, we have dry bulb temperature, and these curved lines are relative humidity lines. And then on the y-axis here, we have the moisture content. So by plotting a temperature and a relative humidity, we can take from the side the physical quantity of water in the air, in kilograms of water per kilograms of dry air. So if we take a cooling example with a dry bulb temperature of 40 degrees, 10% RH, as we start to evaporate the water, you can see the temperature reduces, the relative humidity increases, and the moisture content increases. So that right there is an evaporative cooling process. We cool the air, we increase the amount of moisture that the water is holding. So that very simple process is what we use the whole way through in any form of evaporative cooling. So, as I said, there are three main strategies for evaporative cooling that we're going to discuss. The first is direct evaporative cooling. So here you can see an air handling unit, and on this drawing, it's a double stacked one with a supply AHU at the top and a extract AHU at the bottom. Now, obviously, in real terms, this may be two separate units entirely, but you can see air comes in the left-hand side from the outside air. It passes through an evaporative cooler and it's supplied into the office space. Then that air is then extracted and supplied, exhausted to the outside. So a very, very simple procedure. There are some limitations to it, however. This just shows you moving pictures, you can see it a bit better. Warmish air comes in from the fresh air, goes through the evaporative cooler or the humidifier, supplied into the building, returned out of the building and exhausted. So you can see it comes in warm, it's cooled, it's probably going to pick up some heat in the building from the people, from the machinery, computers, and it's going to go to waste. So a very, very simple process. So in terms of benefits and limitations of this this method of doing it, as previously discussed, you can deliver high volumes of cooling, 0.68 kilowatts per kilogram of water evaporated. So if you consider large air handling units, you may be talking cooling loads in the hundreds of kilowatts required. So for a mechanical cooling system, the energy to do that cooling is quite considerable. But then if you compare that with the energy required to run an evaporative humidifier, you know, you could be talking only one kilowatt of energy to run that humidifier. So in terms of the payback on the system, it's extremely good. You can use this as well for the winter climate. So you can use it for humidification when the outside ambient humidity is low. So it actually gives you two benefits from a single piece of plant. It will give you humidification in winter and it will give you cooling in the summer months. Now, as mentioned earlier, this sort of cooling is really ideal for hot, dry climates because the evaporative cooling principle obviously says that the drier the air is, the more water we can evaporate. The more water we can evaporate, the more cooling we get. So this really is ideal for hot, dry climates where the ambient condition is very warm and very low relative humidity. In terms of limitations for the system, as I said, it's not really suitable for humid climates because if you've got that high ambient relative humidity, you can't get sufficient evaporation to give you the cooling that you need. And you also require quite high ventilation rates, otherwise you're going to start to increase the relative humidity in the building to quite a high level. So just to give you an example of a project we've worked on where we've used this direct evaporative cooling. We worked with an air handling unit company in the UK called Weatherite, who were supplying downflow cooling units to a leading UK telecommunications company. So these units were positioned in their little data halls, switch rooms, that kind of thing. And traditionally they were using compressed type, so DX, direct expansion type cooling systems. So what we did was simply replace that DX coil with an evaporative cooler, as you can see on the pictures here. So there are two ways that these systems were working. The first mode is free cooling only. So free cooling is cooling just by using the outside air. Now you can do this in winter when the outside air temperature is very, very cold. So just by bringing in fresh air from the outside, mixing it with some recirculating air that just to give you the supply temperature you want, you can supply cold air. So in this case, obviously in this situation in mode 1, there's no need for cooling of any sort, whether that's DX or whether that's evaporative cooling. Now, certainly in the UK, when it's cold in winter and sort of the more northern parts of Asia, you're going to get cold winter conditions, so this technique can work really well. But then even in England, we do sometimes get a summer and it starts to get warm, and that means that by bringing in outside air, it's not sufficient to cool the data center. So that's when we move into mode 2. So here, the bypass damper is closing, and you can see the air path has changed. The fresh air is now passing through the evaporative humidifier, mixing with the cooling air, the recirculating air, and then being supplied into the building. So you can see that that means that even in the warmer parts of the year, we can still cool the building without needing traditional cooling systems such as DX or chilled water. So in terms of what this meant to the customer, you can see a comparison here of for a 30 kilowatt cooling system, and in the columns here you have an adiabatically cooled unit, and over here you have a legacy, so the old type of direct expansion cooling that they were using. So you can see for conditions of the year when the temperature, the external temperature was 15 degrees or lower, both systems are running on free cooling. There are some differences in the absorbed power, sort of the amount of power used for the two systems. This is not down to the form of cooling. This is just because, you know, modern technology on the newer units, the fans, the controls, etc., are using less energy. So that's why there's a difference here. It's nothing to do with the form of cooling. It's just the sort of upgrading of the technology elsewhere in the cooling unit. But when the temperature goes above 15 degrees is when things start to get interesting, because we're now using adiabatic cooling instead of direct expansion cooling. So you can see here, this is when we're getting the huge energy saving. So the adiabatic cooler, because it's using a very, very, very small amount of energy, the absorbed power only goes up from 1.589 kilowatts to 1.66 kilowatts. So actually turning on that adiabatic cooler is only a very, very small energy increase. With the direct expansion, it's obviously a much different story. So here we've gone from 2.45 kilowatts up to 23 kilowatts. So 10 times the energy required just to switch on that direct expansion system. So you can see the total annual energy consumption for this customer has dropped from 70,000 kilowatt hours with a DX system down to 14,000 kilowatt hours. So this is obviously a considerable saving. You can see on this graph again a comparison of annual energy consumptions. As I said, when the temperatures are lower, the difference isn't hugely significant. But once you get up to these warm temperatures, you know, the difference becomes absolutely huge. So all in all, the energy consumption by using adiabatic cooling instead of direct expansion cooling is 80% less. So a significant saving for that customer. So the next type of system we're going to look at is called an indirect evaporative cooler. So why is it indirect? Well, you'll notice the main difference between this air handling unit and the other air handling unit is that we've got some form of heat exchanger in there. Now, this could be a cross-flow recuperator, as you can see in here, where the two air paths pass through these heat exchanger blades. But it could similarly be a thermal wheel, a rotating wheel type, or it could be a runaround coil. But there's some sort of heat exchanger in here. And because of this heat exchanger, the air paths are different. So here on the graphic, you can see the fresh air comes in and then it passes straight through the heat exchanger. And then that air is exhausted to the outside. So this unit isn't bringing fresh air into the building. What we're doing is actually recirculating the building air. So you can see the return air exhausted from the building is then supplied back into the building. The evaporative cooler is then put on the fresh air. So what's happening is as the air from the building is recirculating, it's being cooled by the fresh air. So again, in the winter when it's cold, often the low temperature of that fresh air is sufficient to cool that heat exchanger enough to give enough cooling to the building. But then sometimes when the temperature outside is too warm, we'd need to turn on this adiabatic humidifier. So that humidifier is cooling the air and cooling the heat exchanger. But there's no transfer of moisture because all it's doing is cooling the heat exchanger, then being exhausted to the outside. So this gives us a number of advantages really. So firstly, it doesn't mix the air streams. So this is good for a couple of reasons really. Firstly, for sort of secure buildings, data halls where they don't want to bring in a lot of outside air because there's not really the human occupation to need that. It means you don't have to bring huge amounts of fresh air into the building, and you can go into a secure mode. And you know, if there's a fire in the vicinity or something like that, they can lock down the fresh air and they can still maintain the cooling in their data hall just by circulating the room air. Secondly, because we've got that heat exchanger and we're not increasing the moisture in the air that's in the building, we're not having a big increase in the relative humidity. So the ventilation rates are lower by doing that in terms of fresh air ventilation, but we can still have quite a high volume of air circulating and give us more cooling because of that circulation, but without dumping a lot of fresh air into the building. It's really the fact that we don't increase the moisture in the building that's the big advantage in this case. The limitation of this form of doing this is in the efficiency of the heat exchanger. Now typically there'll be somewhere between 70 to 80% efficient, but as a result of that, you're getting slightly less cooling than you would from direct evaporative cooling, but the benefit is that we're not increasing the humidity. So all in all, it's generally worth it. So an example of a project where we've done this is Cork Internet Exchange in Ireland. We worked with an air handling unit company called EdPack to provide cooling to a newly built data center using air-to-air and evaporative cooling technologies. And how this works was as follows. Now bear with me because this diagram can get slightly complicated because it's quite a non-standard design of air handling unit. So we have different sections here. We have a mixing area, so that's where outside air and air returned from the building is mixed, and then the outside air has the humidifier. Then we have a heat exchanger section. Then we have a cold aisle, so that's the air being supplied to the data hall, and a hot aisle, that's the air being extracted from the data hall. So at this point, we'll start adding some arrows. Try and follow them as they start. So outside air comes in, mixes with the exhaust air, and it just circulates round and round through the heat exchanger. So none of this air from the outside is going into the data hall. And then we have a second circulation path round and round the data hall. So it's drawn, the data hall's here, picks up heat through the heat exchanger. It's cooled by this air here and supplied back to the building. So yeah, I appreciate there's a lot of arrows on that diagram, but I hope you can understand the principle of it and the fact that we've got two different, completely separate air paths. That's the crucial thing to understand is this: we have different air paths. The building air is just circulating. The outside air is just circulating on a different circuit. So the next few slides, I'm just going to show you some photographs of during the construction phase of the system. And there you can see the heat exchangers. And then obviously the lower deck was the supply side, and then the extract side up through here. This was the inside of the mixing area here. You can see on the top and the bottom here. Mixing areas again, that's the exhaust air, I believe. So you can see they were quite considerable constructions. They were large units, but obviously that's because they were doing a huge amount of cooling. In fact, each one of these is doing 400 kilowatts of cooling. So that's a considerable amount of cooling. So you can see again, it's a similar pattern here. These bars here is the air-to-air cooling. So as on the previous example, when the temperature is below sort of 15, 16 degrees in Northern Europe climate, we can cool the data hall just by pumping in outside air. But then as the temperature starts to increase up to 30 and higher, we can't do that so much. So we have to start bringing in the adiabatic cooling, which is this portion here. So you can see as well, as the cooling, as the temperature increases, the cooling power needed increases as well, up to a maximum of 400 kilowatts, and the power demand as well goes up as well. So for this particular project, 400 kilowatt units were installed. So the air being returned out of the data hall was at 40 degrees. And by this cooling system, we could cool that air to 26 degrees. The heat exchanger efficiency was 80%. So the electrical consumption for a 400 kilowatt cooling module is somewhere between 11 to 25 kilowatts, with an annual average of 12 kilowatts. So obviously that's a huge reduction in what that would be if it's a 400 kilowatt DX system or chilled water system. And the PUE, now PUE is a metric used in the data center business. It stands for power usage effectiveness. So it's basically a ratio of the amount of the total power the data center is using compared to the power used just for the electrical service. So obviously what they want to achieve is that most of the energy they're using, they're burning in the computers, in the servers. They don't want to be using energy for ventilation system, lights, etc., etc. So the nearer that figure is to 1, the better. And a PUE of 1.4, which is what was achieved for this data hall, is considered to be very, very good. And in fact, for this project, by using evaporative cooling, indirect evaporative cooling, rather than traditional cooling, the energy consumption was 75% less. So the final type of cooling we're going to talk about today is what's known as exhaust air cooling. So the AHU configuration is reasonably similar to what we saw in the previous one, the indirect cooling, in terms of we've got a double decked air handling unit and we've got some form of heat exchanger. But here the humidifier location is different, and crucially the air paths are different as well. So here, fresh air is brought into the unit. It passes through the heat exchanger, the heat recovery unit, but then that air is supplied into the building. So it's not a sealed building in this case. We're still bringing in fresh air. So you might tend to use this more in a building where you've got more human occupants, where you need to have a higher amount of fresh air for their human comfort. And the air is then returned out of the building, and it's here that it passes through the humidifier. So again, we're cooling the return air, which is cooling the heat exchanger, and that exhaust air is then being sent to the outside of the building. So it's not a sealed system, but the benefit is, because again, the humidifier is not on the supply air path, we're giving some cooling, but we're not increasing the relative humidity of the supply air. So we're not making it very hot and sticky in the building for the human occupants, but we're still providing that very, very low energy cooling. So there's a benefit here in that means the cooling capacity is not so dependent on the external conditions and can be used in more humid climates. So what do we mean by that? Now, obviously, again, if it's a more northern climate where we have cold winters, this is good as well, because as well as using this system for cooling in summer, we can also get some heat recovery in winter as well. So when we're extracting warm air from the building and dumping it to the outside, we can warm the incoming air as well. So we're getting a benefit from there. But then in summer, we're getting this benefit of this adiabatic cooler. Now, with this arrangement, you're typically going to need some form of traditional mechanical cooling, because the amount of evaporative cooling isn't as great. So normally that's going to be mounted here on the supply side after the heat exchanger. But that gives us a benefit in a way, because that cooling coil on the supply, it's going to be down at 12-degree dew point perhaps. So that's going to be removing moisture from the air as it's supplied into the building, and you're going to end up with a nice comfortable temperature of maybe 20 to 22 degrees with humidity somewhere between 40 and 60% relative humidity. Now that's perfect for human comfort. So that cooling coil is going to be limiting the relative humidity. So even if it's outside 80–90% relative humidity, that traditional cooling coil is going to be dehumidifying. Because you've got that dehumidification, that means that the air coming back to the adiabatic cooler has got a lower moisture content. So that means that even in humid climates, we can still get a decent degree of cooling out of an evaporative cooler. That then will cool the heat exchanger, which cools the incoming air, which reduces the amount of cooling you need to do on this system. So with an exhaust air evaporative cooler, we're not going to be able to completely get rid of mechanical cooling like we've seen in the other two sorts of system. You're probably still going to need something, but we're reducing the size of that system, so the reduced capital cost because the system's smaller, and reduced energy consumption of that system. So this is a bit of a balance really, but it's the one that can be used more in tropical climates, I would say. An example of a project that we've done is in Germany for a factory for a company called MOBA. So here we provided pre-cooling across 3 air handling units with evaporative humidifiers. to reduce the overall mechanical cooling though. Again, I should stress that we're saying reduce, not replace in this particular strategy. So here you can see a diagram of how the system works. So as I said, the extract air from the building is cooled by a Condair ME unit in this case, and we'll talk about more specifics about types of humidifier later. So the air coming out of the building was 24 degrees at about 60% relative humidity. As I say, that relative humidity is being limited by this cooling coil on the supply air side. So then that humidifier is cooling that air down to 19 degrees C, and it's gone all the way up to 96% relative humidity. So because it's on the extract air and that air is being exhausted to the outside, we can throw as much cooling at that as we want, and we can make that air as humid as you want, and it doesn't matter because it's not going to impact on the people in the building whatsoever. So there we can really maximize the amount of cooling we get. And then on this heat exchanger, we had about 70% temperature recovery, heat recovery. So that's where our initial pre-cooling is happening. So it's reducing the load on this traditional cooling system, and then supplying into the air, into the building at 18 to 20 degrees to allow for some heat gain in the building. So you can see it's going to give quite an advantage to the customer. So if we looked at the some figures now, the operating hours of 8,760 hours per year, an airflow of 53,000 meters cubed per hour. So over the course of a year in the climate in Germany, the evaporative cooling operated for 533 of those hours. Now that doesn't sound like a lot, but it actually, in terms of the cooling for the building, it's quite a lot, because it's Germany. The summer months aren't so long as you might see in other parts of the world. But even still, the total cooling required per year is 63,000 kilowatt hours. Now, for 53% of the year, the mechanical cooling was required. But then for the rest of the year, we can use evaporative cooling and heat recovery cooling. So heat recovery cooling is just using the outside air to cool. Evaporative cooling is obviously what we're interested in, and that was 41.7% of the cooling per year. So if you look at that on a different chart, and the seasonal cooling load performance, the darker colour is the traditional mechanical cooling. So I think it was a chilled water system in this case. But you can see that in the hotter months of the year, significant chunks of that were taken up by evaporative cooling, 40 odd% as it was. So that gave a significant energy advantage to the customer. In terms of what that meant to the customer, so as I said, mechanical cooling was 52.9% of the year, and the energy consumption of that was 10,000 kilowatts. The evaporative cooling was doing 41.7% of the annual cooling, but only for 497 kilowatts of energy consumption. So you can see that's a significant saving. In fact, the overall saving for using this type of system is 45% less energy consumption. Now, in terms of money, you know, as we said earlier, the cooling period in Northern Europe is less. But certainly for warmer parts of the world, this would be very, very suitable. Hotter summers, longer summers, or even places that don't have a cool part of the year. So that energy saving is going to apply to the whole year rather than just a certain proportion of the year. So this is really, really suitable for hotter, more tropical climates. So next we'll look at different types of humidifier that we could use to achieve these three processes. The first is an evaporative media type. So here, this is positioned in the air handling unit. We have a tray at the bottom that holds water with a pump manifold. Water is pumped up to the top here, and it runs down through this glass fiber media. And as the air blows through it, the water is evaporated. So you can get very, very high humidity outputs with these. You know, up to hundreds of kilowatts of cooling through a large system. You know, we've made these things 4, 5, 6 meters wide, 4 meters high, with absolutely huge airflows. So you can do a lot of cooling for a very, very low energy consumption. This hydraulic module here is something like 0.35 kilowatts. And if you can imagine that you could get hundreds of kilowatts of cooling just for 0.3 kilowatt of electrical input plus some water, that's a huge, huge saving possible. They tend to be very low maintenance. They will operate on standard drinking water. So it's very, very simple to just plug and play. You don't have to do too much maintenance on it. Very, very simple system to use. So this probably is the most common type of humidifier used in evaporative cooling system. The other advantage of this is that there's no wet section, there's no droplets being created, so there's no evaporation distance. So because all the evaporation takes place within the glass fiber media, there's no spray, there's no mist. So this whole section doesn't need to be, you know, corrosion resistant, waterproof, etc. so much. I would say that the disadvantage of this type of system is that the control accuracy isn't great, because all you can do is switch on these columns of media one by one. So the typical control is plus or minus 10% RH. But generally, actually, for cooling applications, when we're adiabatically cooling, we just want to throw as much cooling as possible at it. So that, although it's a technical disadvantage compared to other types of system, in reality, it doesn't really matter too much. The next type of system is what is a high pressure spray. So here we have a pump generating water at 60 to 70 bar pressure, so very high pressure. That water is then sent from the pump to this control manifold with stage control valves. So these different valves switch on rows of nozzles within the air handling unit. So by switching on these rows of nozzles, which have different numbers of nozzles on each row in different combinations, we can have up to 15 steps of control with this system. So that gives you a much better control accuracy, plus or minus 5% RH, when compared to the adiabatic system. So that's the advantage of it, and you can use that more to your advantage when you're using this as a humidifier as well. So for when you're using this for winter humidification, you maybe want slightly better control accuracy. That's when you might consider using this system. The installation is a bit more complex because it's a spray system. It has a certain distance required in the air handling unit before this droplet eliminator for the droplets to evaporate. So the section length in the AHU tends to be longer than an evaporative system. Because the nozzles have a tiny little aperture, little hole in the outlet. If you use mains water that's got dissolved solids in it, you would tend to find that there would be blocks with scale, with calcium. So you must use treated water through a reverse osmosis plant that's removed all those dissolved solids. So the capital cost of something like this tends to be a bit higher than an evaporative system that we saw previously. Where this can give an advantage, actually, though, is that you can run multiple air handling units from a single pump station. So we could run up to 4 different AHUs from a single pump, just by having a separate controller and separate valve block on each AHU. So if it's a single system, you know, an evaporative system will be cheaper, a media evaporator, I should say. But if you've got more than one system in the same plant room, then that's where this can start to be a better option. And the final type we're going to look at is what's known as a hybrid spray and evaporative humidifier. So this is using both technologies that we've just seen. So we have a pump system, but this is at very much lower pressure. So up to 7 bar pressure supplied to the nozzles. So the impact of this is that the droplets tend to be slightly larger than what you'd see in the high pressure system. Because the droplets are larger, they take more time to evaporate. So for that reason, as well as the spray manifold you can see here, we have this section here, which is an evaporative manifold. Now it's made of a slightly different material to the evaporative humidifier. It's designed to be really long lasting and hygienic. This is a ceramic material. So whatever doesn't evaporate in this section, and this section is very short, from normally between 600 and 900 millimeters. So you can fit this in a very small air handling unit section, whereas with a high pressure system, you could be talking 2.5 meter section length. Here we're going to be talking a maximum of 1 meter section length, really. And then whatever's not evaporated settles on this media, and then as the air blows through it, is then finally evaporated. So it actually combines the benefits of both the evaporative and the spray systems. We get excellent control because on this system we can go up to 31 steps of control. So that's going to give you control tolerance of plus or minus 2% RH. So we're getting the benefit of the control accuracy that we get with the spray system. But then we get the short section length that we get with an evaporative system because we've got this secondary layer. So we've really got the best of both worlds with this type of system. But all three systems do have their place in the market. So really what you just have to do is look at your particular project and do a comparison of the three and sort of the important factors to help you decide which one's going to be the best fit for your project. Now that's somewhere that your Jeff or your local Condair representative can help you. If you have a project, you can just discuss it with us and we'll go through the pros and cons of each system and help you decide which one's going to be best. So the 5 main sort of factors that we look at are water consumption, energy consumption, pressure drop. So that obviously the resistance created by any component in a handling unit increases the amount of power that the fan uses. So that's why that's a factor. Control tolerance, and then sort of the construction of the AHU. So the evaporative unit has many advantages because it has a low water consumption, because it's just mains water, so there's not the waste of water that you get from an RO plant, plus a little flushing cycle. It has the lowest energy, but it does have the highest pressure drop because you're putting that glass fiber media. So the energy of the fan is going to be higher. So to look at the total energy picture, you need to factor in that. The control tolerance is the worst out of all 3 types of system. But as I say, generally for a cooling system, that's not so important. But then the AHU material can just be standard materials, not stainless steel, because we're not spraying water. So then the 2 different spray systems, the water consumption is higher. The high pressure system has the highest use of water because it's using RO. So some of the water is going to the drain in the RO plant. And then it has a standard droplet eliminator at the back of the section. So whatever water is not evaporated is going to waste. Compared to the hybrid system, it still has an RO, but the eliminator is much more efficient. It's sending a lot less water to drain. So if it's an area where water is a consideration, evaporative should be the first one you're looking at. But if there's another factor that you need to consider, such as pressure drop or control, you might want to consider a hybrid system. In terms of energy consumption, the evaporative tends to be lower. In terms of pressure drop, The evaporative is the worst, but the high pressure is the best. Control tolerance, you can see the numbers. AHU material, evaporative is generally a cheaper air handling unit to construct. So you can see that each particular system has its pros and cons, areas where it's best, areas where it's not quite so good. So as I said, what you really need to be doing is discussing this with your friendly Condair contact, and we can go through the options and really find the best solution for your project. The other service we can offer is a piece of software that we call MyCoolBlue. So this is available as an iPad app and also as a online web via your browser on your laptop. It's not available as an Android app yet, although I believe that is in the process of coming. So this will do modelling for you of exhaust air evaporative cooling. It doesn't cover the other three. This is only for exhaust air cooling. So you can, it's got a load of weather data in there for 300 locations around the world. So if you put in the AHU details, the air volumes, the temperatures that you want, etc., it will basically calculate for you how much cooling you can do throughout the year using evaporative cooling in an exhaust air evaporative cooler, and so you can work out the energy saving over the course of the year. It's quite a cool thing to have a play with. I would recommend you download it to your iPad if you've got one of those, or just have a look on the website otherwise. If you've got a project, it could definitely work for you. The final bit of the presentation is just to tell you a little bit about Condair as a company. We are a fully global organisation. We've got our own sales organisations in many countries. In other countries, we have distribution partners. We've got 4 main manufacturing sites around the world. So we're covering significant parts of the globe, and that's ever increasing. Where we have areas where we don't have representation, mostly sort of Africa, South America, we tend to handle those parts of the globe from here in the UK and Switzerland, which is the part of the company that I really work for, is called the future markets. So it's somewhere where we don't have a office at the moment, but somewhere that we view as a future market. As you know, we have Jeff in Korea, so he will be your go-to man should you have any requirements from Condair. And that ends the presentation. So now I think we're going to move on to a brief question and answer session. I've gone slightly over time, so I do apologise for that. So Jeff, are you there?
Okay, so thank you for your good presentation, Dave, and which I hope it can be very helpful for every attendees today, so that they can understand our main benefits from our Condair evaporative cooling solutions and products. 우선은 그 약 45분 정도 진행된 지금 프레젠테이션을 끝냈습니다. 사실 그 많은 참가하신 분들도 이제 이해하시겠지만 저희 한국 정부가 지금 내세우고 있는 탄소 중립이라든지 뭐 그린에너지 정책, 그리고 이제 각 기업체별로 이제 상당히 이제 고효율 제품, 그리고 이제 에너지 세이빙 정책에 의해서 기존에 아까 데이브 씨가 이제 보여주신 것처럼 기존에 이제 기계식 쿨링 시스템이나 아니면 스팀 그런 가습기를 이제 좀 에너지를 상당히 이제 더 적게 쓰고 있는 그런 이제 증발 가습식으로 많이 바꾸는 게 이제 글로벌 트렌드고, 사실 우리나라도 그렇게 좀 하고 있습니다. 그리고 저희 같은 경우에는 이제 글로벌하게 그 대규모 그 시스템 운영하고 있는 글로벌 데이터 센터, 예를 들면 뭐 페이스북이라든지 구글 같은 경우에 지금 데이브 씨가 이제 프레젠테이션을 보여주신 이 여러 가지 타입의 증발 가습 솔루션을 저희가 직접 공급해서 유지보수하고 지금 이제 계획하고 지금 공급하고 있습니다. 짧으면 짧은 시간, 길시면 길다고 할 수 있는 시간이었었는데, 혹시 그 질문이 있으신 분들은 지금 이제 질문해 주시면은 제가 그 데이브 씨한테 전달해서 직접 바로 이제 피드백을 드릴 수 있도록 하겠습니다. 질문을 올려주시면 제가 전달을 하도록 하겠습니다. 웨비나 툴에서 그 퀘스천 질문할 수 있는 툴이 있거든요. 거기를 클릭하셔서 지금 보내주시면은 바로 제가 볼 수 있습니다. We have a couple of questions from attendee. The first one came from Yoon Soo, has asked, given that Korea's typical summer climate is around 36 Celsius and around 50 relative humidity, based on this, which evaporative cooling strategy is mostly beneficial to them?
What temperature did you say, sorry, Jeff?
Temperature 36 with 50 relative humidity level. This is typical the summer season's condition in Korea. So based on this, which our evaporative cooling strategy is most beneficial?
I think it depends on the application to a certain extent. If you were looking at a data hall, now a lot of data centers tend to be built to the ASHRAE guidelines, which is the American standards that seem to have been adopted across the world for data center construction. Now, a few years ago, they really opened up the limits for temperature and humidity that are allowable. So this was driven really by the actual server and the component manufacturers themselves. They started to say, historically, they would give a very narrow band of temperature they could withstand, and they'd say the humidity needs to be between 40 and 60%. Otherwise, the unit's not guaranteed. But now the ASHRAE standards really opened up on the temperature and the relative humidity. So now they're typically saying between 20 and 80% relative humidity is acceptable. So for a situation like that, where the humidity can go up to 80%, you could possibly look at a direct evaporative cooling strategy using a mix of outside air and direct evaporative cooling. Because if you can tolerate, 70, 80% relative humidity, and your incoming humidity is 50%, you'd be able to get quite a significant amount of cooling within that 30% band that gives you. So for an application where you can tolerate a slightly higher relative humidity in the building, that's an option. If you're looking at maybe an office block or a factory where you've got more workers and you want to keep your relative humidity at a more comfortable band between 40 and 60%, you might look at one of the other options. You could look at the exhaust air cooling, I would suggest, would be a good one for where you want to maintain the relative humidity at a more comfortable level. So it really does depend on the application, but I would suggest one of those two is going to be the right one.
Okay, thank you for your feedback. 금방 이 질문에 대해서 이제 데이브 씨가 굉장히 디테일하게 설명을 해주셨는데, 사실은 우리나라의 이제 그 티피컬한 이제 여름의 이제 외기 온도하고 상대 습도가 30도 중반 내외랑 그다음에 50% 정도를 말씀해 주셨는데, 사실은 이제 이렇다 하더라도 실제로 이제 각 애플리케이션별로 요구되는 그런 상대 습도 세트 포인트랑 그다음에 실내 이제 그 온도가 워낙에 다 다르기 때문에 케이스 바이 케이스 다르기 때문에 실제로 각 애플리케이션에 맞게끔 이제 세팅하는 게 중요하다는 말씀이셨고, 또 실제로 이제 직접 이제 그 증발 가습이냐 아니면 간접 증발 가습이냐, 그러니까 즉 이제 외기에 신선한 공기를 들어와서 쿨링을 할 수 있는 방법도 있기 때문에 이거는 각 애플리케이션별로 좀 다르게 세팅을 해야 된다는 그런 이제 피드백이었습니다. Okay, I have another one question from Min Jae. The question is that is there any hygiene risk can be available or possibly happen? Because for evaporative cooling system, mostly we use the cold the water. So do you think we will be there any risk situation might happen?
Right. Okay. That is a very good question. In terms of cold water humidifiers, we're obviously what we're looking to avoid is conditions where water can stagnate and bacteria can grow. And in particular, we're concerned about the Legionella bacteria, because that will cause Legionnaire's disease, which can be fatal if it's in droplet form. So with any cold water humidifier, there's a number of things that need to be designed into the system to keep the water clean. Now, the first thing is to keep water moving, because if water sits and stagnates, that's when bacteria can multiply. So any system that Condair produce will do exactly that. So obviously during normal operation, it's generally not so much of a problem because the water is being used, so there's a constant flow through the system of water. But it's at the times of year when the system's not working that really the unit needs to do its job. So what it's going to do is, even if there's no demand signal, every 24 hours, it's going to do a purge of the system. So if it's got water in it, it's going to drain that water down and send it to waste. And then it's going to refill with fresh, clean water. So it just keeps that water moving, even at times when the system might not be operating. The other thing that we do with Condair systems is to use ultraviolet sterilization technology or silver sterilization technology. Now, it depends which system you've got as to which one we use, but basically both of them kill bacteria, whether it's ultraviolet light that's used in the evaporative or the high pressure system, or if it's silver, which is used in the hybrid DL system. So both of those systems, basically the water is constantly circulated either through the light or through the silver cartridge, and any water that's supplied to the nozzle or the media has been sterilized. So we know that the water that we're going to be using is going to be clean. So that's what we do on our side. There's a bit of a customer requirement as well in terms of the design of the air handling unit. There needs to be sufficient filtration of the air before it hits the evaporative cooler. So you need some filters just to make sure that there's no particles coming in on the air that may contain bacteria or even just a nutrient for a bacteria to grow from. So if we do our bit and the AHU designer does their bit, we can be happy that we're going to have a clean, hygienic system. But any cold water humidifier that's used should have these things thought about. And those of us that have been around the industry for a while, we've probably all seen systems with mold and green on them, and it's because they don't think of the things that are important, which is to keep water moving and to use some sort of means of sterilization. But with the right design and the right maintenance, it's completely possible to have a hygienic system.
Okay, thank you for your feedback. 저희 시스템은 이제 다른 여타 제품처럼 동일하게 이제 물을 끓이지 않고 직접 분사하는 방식이기 때문에 여전히 물속에서 박테리아가 번식할 수 있는 가능성은 여전히 있습니다. 하지만 이제 그런 부분들을 저희가 이제 해결하고 해서 실제로 예를 들면 이제 24시간 내에 시스템이 이제 운영을 하지 않는다든지 정지인 같은 경우에는 물을 이제 배출해서 다시 배출된 물만큼 다시 신선한 물로 채우는 그런 시스템을 가지고 있고, 그리고 실제로 여러 가지 필터를 써서 UV 필터라든지 음이온 필터를 써서 물속에 있는 박테리아를 이제 멸균을 하는 그런 처리 과정을 통해서 저희가 이제 수질을 항상 리스크 없는 그런 이제 상태로 저희가 유지를 하고 있습니다. 그리고 또 하나 말씀드리고 싶은 거는, 물론 이제 공기 중에서 있는 박테리아가 직접 유입이 될 가능성이 있기 때문에 실제로 이제 고객사 측에서 깨끗한 공기를 이제 유입될 수 있도록 하는 그런 추가적인 그런 조치도 필요하다고 생각됩니다. Okay, we have another one question from Heinz Rauner. It's about seeing over all system and strategies, which cost of ownership is the lowest for a certain combination of temperature and humidity.
Can you repeat the question, please?
Yes. Seeing over all systems and strategies, which cost of ownership is the lowest for certain combination of temperature and humidity?
Difficult question. I mean, in terms of the humidifier itself, it's going to be the same for all of them. I suppose what you need to do is look at the pressure drop. I don't think there's a great difference between all of them, actually. Mm-hmm. Do you mean the humidifier itself or the three forms of evaporative cooling? What's the question?
So if we consider all the systems and strategy, so the point of the question was, which cost of ownership it will be the lowest for a certain combination of the temperature and humidity, if you consider every possible condition?
It's very difficult to do that because each system has its own particular areas where it will be the best and areas where it wouldn't be quite so good. So it's very difficult to answer that question, quite honestly.
Mm.
There's too many variables. You can't say one is, because there's too many variables. You know, energy consumption, water consumption, the temperature, the maintenance on other components in the air handling unit, the maintenance on the humidifier. There's too many variables to say that's the one. As I said, you have to look at each project on an individual basis and discuss it with your local Condair representative, and you can start to work out which of the factors are the most important for this particular project.
Okay, I think yes, for this question, since we needed to prepare something, because this is quite wide range of the question that we need to consider everything more widely. So if applicable, we will contact you, Rauner, and we'll send you our feedback later on.
Yeah.
Okay. So is there any other question? Okay, so no question has been raised until yet, except those previously asked 3 questions. So, okay, so thank you for all the attendees and your time. Okay, so 지금 45분간 좀 넘게 사실 1시간 정도 지금 진행을 했었는데요. 굉장히 짧은 사실 프레젠테이션일 수도 있는데, 아무튼 저희가 가지고 있는 이제 증발가습 솔루션에 대해서 장점을 실사례를 들어서 이제 설명을 드렸고, 아마 이 프레젠테이션을 통해서 가장 핵심적인 그 베네핏이 어디서 오는지를 아마 조금이라도 이해를 해주신다면은 그게 저희가 바라고자 하는 가장 큰 성과가 아닐까 생각합니다. 사실은 저희가 이제 첫 번째로 지금 웨비나를 열어드렸는데, 앞으로 아주 관련된 여러 다른 이제 주제를 가지고 순차적으로 계속 웨비나를 할 예정이고요. 그리고 이제 가능하다면은 지금 오늘은 이제 데이브 볼 씨가 직접 영어로 진행해 주셨고, 다음번에는 가능하다면은 한국어로 된 그런 웨비나도 저희가 준비하고 있으니까 많은 관심과 성원 부탁드리겠습니다. 아무튼 오늘 1시간 조금 넘게 참여해 주시는 모든 참석자분들한테 감사 말씀을 드리고, 오늘 웨비나는 여기서 종료하는 걸로 하겠습니다. Okay, thank you for every attendees for your time today. So I hope this webinar can be a benefit to all of everybody. So we will keep continuing to another following webinar soon. So I hopefully to meet you again on another web based seminar. Okay, thank you for your good presentation, Dave. And okay, it's time to wrap it up.
Yeah, thank you for the invitation to speak. It's been very enjoyable. I hope everyone's got something out of the session. If you've got any questions, you can address those via Jeff. So thanks for your time.
Okay, thank you. And 감사합니다. 오늘 웨비나를 여기 종료하겠습니다.